The next speaker is Courtney Shafer from the University of Buffalo. She studies glaciology. Her advisor is Kristen Poinar. And Courtney's done 2 practicums at Los Alamos National Laboratory. Let's welcome Courtney.
Hi, everyone. It's so great to be here. It's kind of weird standing up here as a 4th-year fellow, but let's get started. So yeah, I'll be talking about investigating the impact of ice shelf cavities on Antarctic sea level rise projections. Okay, so hopefully many of you know that mass loss in Antarctica is accelerating. Since in the last 2 decades, since 2001, mass loss has been on average 142 gigatons per year. The previous 2 decades prior to that were 48 gigatons a year. So this is an increase of almost 200%. Most of the mass loss is happening here in West Antarctica, and in this region, ice is sitting on bedrock that is below sea level. And so as the ice flows out, it flows out into the ocean and it floats on top of the sea. And so what we call these are ice shelves. And these ice shelves are critical to the control of mass loss, specifically because they are melting from underneath. And so what happens is this warm ocean water called the circumpolar deep water current will come in towards the grounding line, which is the point where the ice becomes floating, and it will melt the water, it will melt the ice, generating fresh, cold water that will generate a rising turbulent plume that further entrains warmer water and melts the underside of this ice shelf. And so it's not the melting of this floating ice shelf, right? Archimedes' principle, whatever is, if you had an ice cube floating in water, it's not actually going to contribute anything to sea level rise, but it's the weakening of this ice shelf that's reducing the back stress felt on this ice sheet. And so it allows the grounded ice to further accelerate into the ocean, raising sea levels. And so while we know that sea level rise is occurring and these ice sheets are melting, we actually don't really know how much Antarctica is going to contribute to future sea level rise. So this is a figure that's showing multiple ice sheet model projections that are forced by various Earth system models. And by 2100, you're seeing projections of -7 centimeters all the way up to 26 centimeters. And so the reason for this large discrepancy is because most Earth system models don't actually resolve these cavities. They don't resolve the ocean processes that are occurring within these cavities. And what usually happens is that the ocean domain within these Earth system models comes right up to the ocean, right up to the ice shelf front, and then it just stops, creating this imaginary wall. And so you'll miss this entire circulation mechanism that occurs beneath these ice shelves that's critical to this melting of these floating ice shelves. And so this kind of motivates 2 questions, and the first one is, what is the error that's introduced on Antarctic projections when we exclude these ocean conditions beneath ice shelf cavities? And another way that we can phrase this is, how well do most Earth system models perform today? Well, we need an Earth system model that actually resolves these cavities. And fortunately, we do have one of those. The Department of Energy's Earth system model, which is the Energy Exascale Earth system model, which is a global scale model of many different components, including an ocean model that was recently updated to include these cavities. And so, great, now we have an Earth system model that has cavities. And so now we can run this Earth system model forward for 100 years from 2000 to 2100 under a moderate carbon emission scenario. And we can generate ocean outputs from this Earth system model, so temperature and salinity of the ocean, with that information included in cavities. So we can take all those ocean outputs and we can create 2 different experimental configurations. And the first one is going to be the case where we include these cavities, we keep the cavities, And the second case is one that I'm constructing. So in this case, we're masking out those those cavities beneath the ice shelves to mimic how most Earth system models work today. Then we'll parameterize melt rates from these two different configurations. Right here this is just the ocean information, but we can take the ocean information and we can parameterize melt rates from that. And then we can use those melt rates and force an ice sheet model with that evolving basal melting information. And again, this ice sheet model is going to run forward from 2000 to 2100. And so this kind of configuration, or this kind of modeling experiment is what's known as a standalone ice sheet modeling experiment, where we have the Earth system model running first, and then we give those outputs to an ice sheet model separately. And so first I'll talk about how we parameterize those melt rates, and then later on I'll talk about the results from the ice sheet model. Okay, so parameterizing the ice shelf basal melt. Again, we start with our ocean information from E3SM. We create our two different configurations. Again, we're keeping ocean information in the cavities. The second one, we're masking them out. Okay, now we need to extrapolate. So remember the case where we don't include, the case where we're masking out ocean information within cavities, we still need some idea of ocean information beneath these ice shelves. We can't just have a void beneath these ice shelves. So we need to extrapolate in. And if you'll notice, I'm also extrapolating beyond the grounding line. And this is, we do this as well to account for ice sheet retreat. So as these ice shelves are melting, the ice sheet is going to retreat. We want it to retreat into regions that still have real ocean information. Right, yes, so we're flood filling in, we're also filling beneath. And we do that again, same for the case where we do include cavities as well, but this time we're extrapolating from the ice shelf base again, further beyond the grounding line to account for ice sheet movement. Okay, so we have those two cases, and now we're going to parameterize basal melting. So this is just a simple relationship. On the left-hand side is the parameterized melt. On the right-hand side, it is a function of the difference between the ocean temperature and the freezing temperature at a specific point. So in the ocean, the freezing temperature is not always necessarily zero. It depends on density and salinity. So this is basically telling me how much of the temperature is available to melt the ice. Okay, so now we've got our two parameterized melt rates for both configurations. We're going to give it to the ice sheet model, and the ice sheet model is going to run forward from 2000 to 2100. So I'll be focusing on the dark pink and the dark green projections, but we also run controls for both of these configurations using historical conditions. That's just a way to confirm that our projections are making sense. Okay, so before I show you what the response of the ice sheet looks like, I'm going to talk about the basal melting that we get. That's parameterized from E3SM. Okay, so this is showing a time series of the ice shelf melt. In pink, again, we have the configuration with no cavities, where the ocean information is masked out. And the green is the case where we kept the cavities. So you'll see that in the pink case, but around year 70 or 2070, we separate here, and we're seeing more melting occurring for the case where we don't include cavities. And that persists all the way to 2100. So yeah, around 2070. So for both of these scenarios, melt rates are increasing. They're quite similar until 2070, but the configuration without the cavities is having more melting by 2100. So we could visualize that more spatially. So on the left-hand side here, I have the change in melt rates from 2000 to 2100 for both configurations. We're seeing elevated melt by these red spots in both West Antarctica and East Antarctica at these ice shelves. But I'm more curious of what the difference, I'm more curious about which configuration is contributing more. So I take the difference between these two cases, and I see, anyways. yeah, I see that these bright pink spots, which are associated with the configuration where I excluded the ocean conditions within cavities, is showing a larger increase in melting in that configuration. So yeah, so again, a larger melt rate increase for the case where we're excluding those cavities. So right, these are just the melt rates that were parameterized from E3SM. So now I'm going to show the response of the ice sheet model from those melt rates. So on the left-hand side is the ice sheet thickness change. So again, top is no cavities, bottom is cavities. Very dominated by red, so we're seeing a lot of thinning for both of these cases. But again, I want to see which configuration is contributing a larger thinning signal. And again, it's the case where we exclude those cavities. Lots of pink happening in all of these ice shelves around Antarctica, specifically in East Antarctica, which is interesting. So Amory, Drowning Maudland, Totten is experiencing greater thinning in the case where we exclude cavities. Okay, so right as the ice sheet is thinning, all of that mass is going to contribute straight to the sea. So we can see the impact on sea level rise. So basically right here, we're seeing a little bit of a greater contribution to sea level with the case where we exclude cavities than the case where we include cavities. And these are our controls. So the difference is about 14%. It's actually not that large. These, if you squint, I mean, these lines are basically the same. So what is the error introduced? It's about 14%. And how well do these Earth system models perform? The ones where they're excluding these ice shelf cavities, I would say they're performing pretty well. If your geometry isn't evolving drastically, right? So these simulations were done out to 2100. Your ice shelf cavities are not evolving that much. Your grounding lines aren't evolving that much. If you had a scenario where your ice shelves are completely collapsing and the geometry is drastically changing, this assumption breaks down. So in that case, you would definitely need an Earth system model that has a fully coupled ice sheet model component to be able to capture the interactions and feedbacks between all of these different components. Okay, so summary. Again, ice shelf basal melting is really important for the stability of these ice sheets. But most Earth system models don't include that mechanism. They don't include the circulation mechanism beneath these cavities. And so our comparison experiments show a slight overestimation, but not by much. So this is reassuring, right? Earth system models and ice sheet models that don't yet include cavity information, ocean information beneath these cavities, can still participate in these large collaborative modeling efforts if you're making projections to 2100, right? But you would definitely need a two-way interacting ice sheet model component within a full Earth system model if you wanted to actually capture those feedbacks between the ice and the larger climate system. And so I just want to thank all these people that made this work happen. On the left-hand side are all my collaborators from Los Alamos. A wonderful team. They've been so supportive. I couldn't have asked for a better group to work with. On the right-hand side, I have my advisor, Kristen, and my committee members. Then, of course, Dan. Thank you for giving me a job during the pandemic. That was great, and for introducing me to ice sheet modeling and just for being an awesome mentor during this time. So, and big thanks to CSGF for making all this work possible. Thanks.